Welcome. So this is going to be very fast. I will be very fast. I do have a lot of content. So today I'm going to talk to you about our efforts in accelerating bioinformatics workloads. Although I made an earlier presentation last year, but I tried to update it for this year. So since in CGSI we do not introduce speakers, but speakers introduce themselves. I got my PhD from Case Western Reserve University under the supervision of Cenk Şahinap, and then I did a lengthy postdoc with Evan Eichler. And since then, we have been working on developing different algorithms for basically genome analysis, mapping, variation discovery, alignments, and so on. And more in the last few years, our efforts has been shifted to accelerating bioinformatics workloads. So right now, I would say about 70% of our work is in algorithm design, and about 30% is in hardware acceleration. Today, I'm going to more focus on read alignment. As we know, when we are aligning billions of short reads or hundreds of millions of long reads, what we do, the alignment process is pretty slow. And the reasons for this that my former student Mohammed Alser characterized was that the 93% of the read mapper's execution time is spent on the alignment. This is Needleman-Wunsch-Smith-Waterman or derivatives of it. And another observation that was that since we are doing seed and extend based alignments, which is finding short exact matches quickly in all one time, and then extending it with Smith-Waterman and derivatives, about 98% of the original seed locations were actually non-verifiable. So this is before the time of the minimizers and chaining, which also supplies some cleanup of these potential locations. And finally, Smith-Waterman is slow, right? Needleman-Wunsch is slow, so this is an n squared time dynamic programming algorithm, and for the optimal case, you have to calculate a lot of different values. There is a lot of data dependency. This is in here too. So to be able to calculate, is my mouse visible? Okay, so in order to calculate this 5, for example, you need the values of this 4, 4, and this 5 as well. Right? So this is quadratic time, although we have to do what we have to do. All right. As I said, we tried to make this faster, and over the years we have developed different methodologies, CPU and SIMD based acceleration methods, moved into the FPGAs and GPUs later on, and then we started also to play with processing in memory. So these are the old days. So I'm just highlighting 2 of my former students who have been at CGSI before. Mohammed is going to join Georgia State University as an assistant professor in a few months, hopefully. So he was the first student in my group working in GPUs and FPGAs, main FPGAs, to accelerate the alignment process, which we call the pre-alignment. So this is basically getting rid of unextendable potential seed matches very, very quickly. Right? And then Zülal extended this GateKeeper algorithm into GPUs, and she also improved the accuracy a little bit as well. So what we want to do these days is that we want to accelerate mapping and filtering and also the alignment algorithms. So we are starting with these, but we are going to also work in different bioinformatics workloads as well, using in-memory technologies. Right? So this is the processing in-memory technologies. So what is processing in-memory? It's an upcoming technology. It's still in the development level. So they are available, but they are not available widely. So basically, what it is, it stems from the cost of energy and runtime when we are doing data movement. So if you remember your introductory computer architecture courses, computer organization courses, is that we have CPU, right? And we have main memory. And between the main memory and the CPU, we have level 1, level 2, level 3 caches. And the data stays in DRAM, and then it's moved to those caches. and then the calculation is done in the CPU, and then the data moves back to the DRAM, right? So there is a lot of going back and forward. So this is the study in 2018 our collaborators did. They realized that about 93% of the total system energy consumption is wasted in data transfer in the memory bus. Right? So this is between the CPU and the main memory. Right? So one potential solution is to move the computation close to the data. So here the CPU is on the far left side, the DRAM is on the far right side. So we just put some compute unit right next to the memory, which is basically the processing in memory technologies. Right? So one challenge here is that this is a limited area, so these new compute units are not going to be as full as the CPU, so they are not going to be doing everything, but they are going to do something. Hopefully the things that we are going to, the instructions that we are going to need the most in our applications. All right, so these are some of the processing in memory technologies that are currently under development. I'm giving actually two examples here. The top, where is my mouse here? So this side is the hybrid memory cube technology. So this is basically when we have a DRAM, for example. So this is more similar to a DRAM. You know that we have these chips which actually stores the data. You put them on top of each other, layer them up, right? And then at the bottom layer you add some additional circuitry which is going to be your compute unit. And in that unit you are going to implement some of the instructions that you need the most. Right? And one thing here is that when we are layering them up in a 3D stacked fashion, there are also fast data transfer between them through which are called the TSVs or the through silicon vias. Another technology that we are currently working with is from a French company called Upmem, and they have developed this hardware called DPUs. And again, they are similar to the traditional RAM. So we do have the RAM chips, but DRAM chips are right next to the DRAM chip. There is a DPU. There are different models of these, but some of the high-end models have more than 2,500 DPUs. I believe they are data processing units. They are called the data processing unit. So they have direct access to the DPU, to the DRAM. And then the DRAM is also structured in a way that there are caches within the DRAM, which is called the working RAMs or the WRAMs. These are the current technologies that are being developed, but we started working in at least in simulation fashion earlier than that in 2018. So this is work from Jeremy, who did his PhD in ETH Zurich, and he developed a filter called Grim filter. So this is, again, a PIM approach, although it was always in simulation. And the key idea was to exploiting the high memory bandwidth to get rid of the unextendable regions. So again, when we have a seed and extend, we usually find very short matches. Let's say k is equal to 12, like 12 exact matches in one time. But then our read is much longer than that, usually like 100, 150 when we're dealing with Illumina. Then it calls the Smith-Waterman alignment. So we do have like 88 more basis information in there, right? Basically, it is a processing in memory technique. It provided more than fourfold speed up or up to like sixfold speed up compared to the CPU implementations. So here's the idea. Again, we have the 3D stack memory. So we have the DRAM layers, and at the end, we have the logic layer, right? And then in the logic layer, so the DRAM layer is organized as banks. Again, this is from your computer architecture courses. And in the bank is an array of cells with row buffers to be able to transfer data. Right? So what we do with green filter is we create some bit vectors and then we lay them out in the banks in an efficient way so that we can perform calculations fast on them. So these bit vectors are going to be put in those banks in the DRAM chips. So here is the idea. So let's say we have this reference genome, and then we are going to divide it into bins, into overlapping bins. Right? Here we are showing 4 different bins that are overlapping with each other. Right? And then we are going to represent each of those bins with a bit vector. And then in this bit vector, we are going to basically keep track of which k-mers are within that bin. Right? So typically these bins are, I believe in that paper it was about 200 base pairs long. And then let's say for our k-mer size is 5. So we are just keeping which 5 mers are in each bin. Right? Which gives us a bit vector. So this is the first bit vector for the first bin. Basically, it says there is A is in this bin, right? So this is just 0 and 1. These are not k-mer counts. These are just occurrence, much like balloon filters without the hash function calculation. We have CCCT in this bin, but we do not have any AAAG in this bin. Right? So when there is a read coming in, and then let's say the initial hit is in the first bin, we also look at the k-mer composition in that read, and then we also query that k-mer composition in that bit vector of that bin. Right? So quickly. So here it does not use any location information or the relative locations of those k-mers within the read. It just looks at the composition. So again, AAC here is in here, but TTT is not in here. Right? So again, we are going to just quickly search for the k-mer composition. If the k-mer composition is high enough, then we are going to do the alignment. If it's not, we are going to just discard that alignment. So basically, storing all bit vectors in this fashion is going to require 4 to the power k times b bits in memory. So we have b bins, right? And the length of the k-mers are k. So if we are searching for k is equal to 5 and bin is equal to 200, then the required memory footprint is going to be less than 4 gigabytes, which is actually not that much considering the amount of memory that we waste these days. Right. Okay, so these are those bins, and then so on. So then, again, the green filter just looks at this k-mer composition very, very quickly. And if this is our input sequence R, we get those tokens, and then we read the potential bit vector, and then we match those tokens to those bit vectors, and then we do a sum. Right? How many of those k-mers are in this bin? That is basically just looking at those and then adding up those ones that hit our k-mer composition. Obviously, we are not going to take the third one in here. And then we compare it against our edit distance threshold, and then we decide whether to proceed with the alignment or not. All right, so since these are all done in bit vectors, it only requires very simple operations in here. So that summation is very similar to the pop count available in your CPUs as well. And it is also very highly parallel. You can do this for each bin at the same time. They are all operated on separately and independently. And it is also memory bound. So that is a lot of work is done in the memory, which gives you a good opportunity to actually implement this in 3D stacked DRAM architecture. Just very, very quickly, Damla also developed another algorithm called GenAsm. So this is not specifically PIM. It's not specifically processing in memory technology, but again, PIM-friendly algorithm, which extends the BiTAP algorithm. Right? For those that are not familiar with BiTAP, it's also called the shift-and method. It is developed for existing search in 1964. And then it was extended to use mismatches and wildcards in 1989. Index were added into the algorithm in 1991. which is part of the AGRAP tools, which is available in most Unix systems. Right? More improvements comes from by Zayas and Navarro in 1996. And then what Damla did was she added the capability for tracing back, and she also reduced data dependency when calculations, and therefore provided acceleration. So this thing took 56 years in the making. Okay, so if you haven't taken introductory bioinformatics courses, these are, I believe, available in all of Pavel Pevsner's textbooks. The shift and method or the BiTAP method is it available. I think I stole this slide from you. So when we have a text and pattern, so here the pattern is 4 and the text is California. What we do is we generate this bit array or bit table. In reality, it won't be a table. It will be just, again, 2-bit vectors. Is that when there is the position ij is equal to 1, it means the first I characters of P exactly matches I characters of T ending at character J. So when we have a perfect match of 4 in California and then we have this set to 1, that means the first 3 characters of 4, right? The first 3 characters of our pattern 4 matches our pattern, our text ending at position 7. Right? And these are again bits, so we can also calculate these very, very quickly. And for this, we need one operation called the bit shift, which is looking at the previous column, we shift the bits by 1, and then we set the topmost bit to 1. And we also have additional bit vectors that represent the pattern. So if our pattern is ABAAC, for example, and our alphabet has ABC, we need 3 bit vectors UA, UB, UC, which is going to show you the positions of those characters in the pattern. And then the table is calculated by this. Right? So again, you don't need the full table. You only need 2 vectors for every 2 columns that you're going to process. And once you have an MJ is equal to 1 at the last row of the bit vector, that means that you have a perfect match. Again, this is very quickly calculatable, although theoretically it is still quadratic runtime or theta event runtime. It is in practice very fast because you are only dealing with bits. So Damla took this approach, and then she also added algorithmically the traceback option, which was not available before. And then she developed the GenAsm structure, GenAsm framework to accelerate this ideally in memory, but again, this is also implementable in FPGAs. I'll just skip this quickly because I am pretty sure I'm going to be over time. This is a modified PIM-friendly BiTAP algorithm or the shift-and algorithm. And then we modified the baseline algorithm to provide to also enable efficient alignment for longer patterns. So for efficiency in BiTAP, it should be 1 or 2 computer words, which is 1 word is 32 bits. For longer sequences, you need more tricks, which Damla provided. And she also removed the data dependency between those iterations and provided parallelism in these operations. And then this bit shift is all implementable in using simple shift and OR gates. Right? So she also extended this later to provide accelerators for sequence-to-graph alignment. Okay? And by the way, all of her talks are available on YouTube if you're interested in more details, and my slides are going to be available on my website as well. So she developed this tool called the SeGraM. So this is an extension of GenAsm. This time it's not sequence-to-sequence, instead it is sequence-to-graph. And you probably heard of the pangenomics, which is the current hot topic in genomics. So we are not going to compare against one linear reference genome. Instead, we are comparing against many references represented in a graph. Therefore, her second algorithm, SeGraM, is an acceleration for the sequence-to-graph mapping. So for this, the accelerator is composed of two parts, min seed and bit align. So min seed is basically a hardware implementation of the minimizer extraction step in Minimap 2, right? So algorithmically it's not different. And bit align is an extension of the GenAlsem method into align into sequence graphs, right? And those graphs in that study were generated by VG, the most popular variate graph tool today. So again, she gained a lot of speed up. So up to 100-fold speed up compared to, for example, Graph Aligner. So I am not exactly sure which one was which. I think the 6-fold speed up was for Illumina, 100-fold speed up for PacBio Hi-Fi, or the other way around. But we tested, both those. So we do have a lot of speed up and also a reduction in memory, data movement as well. Okay, again, this is also available in YouTube. Okay, so starting from these, right, there was a new project that we wrote, which came out of boredom during the COVID lockdowns, literally. I was at home, I was bored, I opened my laptop, I started emailing my friends, Ryan being one of them. Also Onur Mutlu from ATI Zurich and the others, and then Ryan invited somebody, Dominic invited Abmem, and then our family grew in the matter of like 2 days, and then we wrote the grant in the matter of a couple of weeks, I think, got rejected, revised, got accepted. Right? So the BioPIN project is a Horizon Europe funded project composed of 8 different participants. Me, ATA Zurich, Ryan from Institut Pasteur, CNRS Dominique, 11 years, IBM Research Zurich, Technion, Israel, UPMAM, France, and Bar-Ilan University, Israel as well. So our aim was to leverage these emerging processing in-memory technologies, and we have the chance that here the UPMAM is part of us. They also develop processing in-memory technologies. And IBM Research also develops in-memory processing in-memory technologies as well. So our aim is to accelerate alignment and search, pangenomics applications, global and local assembly, and variation calling and base calling. So these are all within our aims, while providing cost, energy, and time savings. So for reporting purposes, we came up with a number of publications recently. So I think people are over-reporting those. So there are like 40 papers that we reported, but a lot of them forgot to actually acknowledge the project. So more realistic number is somewhere around 20 in 2 years, by the way. Okay. Okay, so this is the structure of the BioPIN project. It's composed of different work packages. So what we did was, first we did some analysis of the runtime, some runtime analysis and memory pattern analysis of existing tools and tools and data structures. And then we started to map those algorithms into different in-memory technologies, specifically the 3D stack memory and the DPUs. And also our collaborators from Israel, Bar-Ilan, they are also developing processing using memory designs, and they are more electrical engineering. So there is lots of Kirchhoff rules and memory, the electric resistance stuff going on in there, which I am not really very knowledgeable at. Right? So it is the real engineering part. And part of this is also developing PIM-friendly API design and software integration as well. So I'll just give some very basic overview. As I said, we initially analyzed some of those tools. So we see that, for example, BWA MEM is about 40% memory bound. So that is, we are wasting about 40% of our time waiting for the memory for the data transfer. In Graph Aligner, so Graph Mappers, Graph Aligner was the worst, almost 60% memory bound. We also look at MeshMap, which was not that bad. So it was more core bound than memory bound. So core is the CPU. And we also look at some long read sequence mappers, And among those, LRA was the most memory bound compared to the others. So looking at those, one of my students, Ömer, is now working on a sequence to graph alignment tool. So first he analyzed these existing tools, and then one thing we also saw that graph alignment was the worst in terms of memory boundness. And this was the instruction from VG, for example, this is from VG, not from Graph Aligner. But the graph Smith-Waterman function here is the one that spends the most time in the CPU. Right? So these are potential targets for us to accelerate. So this is current design, which is not yet implemented, but the idea is to divide the graph. So since this is graph and the graphs are large, right? And in the DPU architecture, in UpMem DPU architecture, every DRAM chip is only 64 megabytes, and every DPU can access to only one DRAM chip. So you have to divide your graph somehow into chunks of 64 megabytes to be able to process each read independently from each other, right? So this requires some graph partitioning, hopefully with some overlap, so that we don't miss across partition mappings, and then the rest is going to be done by the DPUs, and then it will be reported back to the CPU for reporting. I already got my 5 minutes mark, but don't worry, I am almost done. So I'll just give some samples of our bioinformatics projects. As I said, there are 20 to 40 of them in the last 2 years, more coming, obviously. So here is an example from CNRS, from Dominique Levanier's group. They developed a needle movement acceleration using DPUs. And they had some decent speed ups with 40 ranks of DPU. This is not using the entire 2500. They achieved about 10-fold speed up when aligning 16S ribosomal RNA sequences. They also did some pack bioalignment analysis, and they have seen about 8-fold speed up compared to Minimap2. Another thing that they also tried was balloon filters, and they achieved some modest improvements, 2 to 3-fold achievements in balloon filter construction and query runtimes. So this is more modest, but now we are also working in ways to still make use of this to accelerate some other methods that also use balloon filters. ETH is doing a lot, so out of those 40, 35 of them are from ETH. So they are doing different things. So they are also working on in-storage processing as well. So in the SSD disks, for example, there's a controller in every SSD disk, right? So these are hard disks. So they are also using the controller to do acceleration in computation. So they also do what is called the processing in flash. So for the flash memory, again, the SSD disks, so they modify the bits basically in those flash chips in the SSD disks to achieve speed ups. So they have developed many different designs. One of them, I think it will be published soon, is doing accelerated in-storage metagenome analysis. So they also do some metagenome composition analysis in storage in the disk. Another example from GAPIM. So this is from Barilan. Again, this is more electrical engineering, so I don't know what really is going on. But this is for the discovery. So this also includes the pair HMM method from GATK. So this is basically a GATK accelerator, right? Pastors, they are also developing a bunch of different things. Ryan is here, so I just wanted to highlight this one, which is a BioPIM programming library. So they are working on an API, a C++ API, to make these easier to program for those that are not really very knowledgeable about underlying architecture. Right? Here is just one toy example. So this is a checksum. So this is just adding up all the bits in a bit vector. in DPU, and all you have to do is, so this is just regular C++ code, right? So this is just simple sum them up. And then what you do is you just put this into a BPL launcher, and then you say arc upmem, and then it just launches into the DPU, and then you collect the data. One thing that I omitted here, if you just change this from Arch upmem to Arch multi-core, it becomes a multi-core. Okay, so it's not necessarily for upmem only. Okay, so IBM is working on neuromorphic computing, so they are accelerating neural network analyses. So they are focusing mainly on base calling for nanopore in RNA accelerator, but no more details on this because I'm scared of IBM lawyers. Okay, I actually asked for permission so what I can show. They still didn't respond, so I'm not going to show them to you. But they are working on neuromorphic computing angle as well. So finally, I would like to thank my group. So two of them are here. Also my collaborators and also my founders, and also Ryan is here. Two of my students, Clea and Ricardo, are both sitting right there. Before we go, about CGSI, you all have received your T-shirts. Do not forget to use them and represent in Thailand in a beach. Why not? Thank you.